I am Jeric M. Eduarte, a Bachelor of Science in Information Technology student of Davao del Norte State College, and I am going to have a visualization about the Dijkstra shortest path algorithm.
Dijkstra's shortest path algorithm was invented by the late great Edsger Dijkstra, a famous Dutch computer scientist. The objective of the algorithm is to find the shortest path between any two vertices in the graph. In fact, Dijkstra's algorithm will find the shortest path from the given starting vertex to every other vertex to the graph.
Consider this simple graph. Our objective is to find the shortest path from A to every other vertex. Once our implementation is run, Dijkstra's algorithm will generate this information which has the data accessed in the graph. We have the shortest distance from the starting vertex to all of the other vertices. The total shortest distance from A to G is 5. From A to J, it's 10. From A to K, it's 2. And from A to M, it's 4. We also have the shortest sequence from A to every other vertex, which tells us the shortest path. For example, to get from A to J, notice that we arrived at J via M, which is shown in the previous vertex column. When we check the information for M, we can see that we arrived at M via K. And when we check the information for K, we can see that we arrived at K via A. So the previous vertex column actually gives us the shortest path from A to every other vertex. So how did Dijkstra's algorithm generates this information? Dijkstra's shortest path algorithm works as follows. We are using two lists, one to keep track of the vertex we visited, and another to keep track of the vertex we haven't visited yet. So let's consider the starting vertex, vertex A. The distance from A to itself is 0, because there are no other edge that vertex A points to itself. And the distances for all other vertex from vertex A are unknown. Therefore, for the meantime, we will set them to a higher value, infinity, and then include this information to the table right away. Now, we will visit the unvisited vertex with the smallest known distance from the start vertex. First time around, our starting vertex will be A. For the current vertex, examine its unvisited neighbors. Well, since we are visiting A and its unvisited neighbors are G and K, these are the vertices that A shares edges with. For the current vertex, we calculate the distance of each neighbor from the start vertex. The distance from A to G is 0 from A plus 7 is equals 7. And from A to K is 0 from A plus 2 is equals 2. If the calculated distance of a vertex is less than the known distance, we can update the shortest distance in our table. At the moment, all of the shortest distance are infinity. So we can update these two distances. Now, we update the previous vertex for each of the updated distances. In this case, we visited G and K via A. So we will write this information to our table. Now add the current vertex to the list of visited vertices. We won't be visiting A again. Now the algorithm begins to repeat. Visit the unvisited vertex with the smallest known distance from the starting vertex. This time around, we can see that it is vertex K. For the current vertex, examine its unvisited neighbors. Well, since we are visiting K and its unvisited neighbors are G and M, which vertex D shares edges with. The distance from K to G is 2 from A to K plus 3 is equals 5, and from K to M is 2 from A to K plus 2 is equals 4. If the calculated distance of a vertex is less than the known distance, update the shortest distance in our table. The shortest known distance from A to G, as written in the table, is 7. We just calculated a new shortest distance of 5. The shortest known distance of E, as written in the table, is infinity. And again, we calculated a much shorter distance from A to M. So we could write this information to the table, replacing the previous values. We found some shorter path. Now we update the previous vertex for each of the updated distances. In this case, we visited G and M via K. So we write this information to the table. Add the current vertex to the list of visited vertices. We won't be visiting K again. Once again, visit the unvisited vertex with the smallest known distance from the starting vertex. This time around, the information tells us that it is vertex M. For the current vertex, examine its unvisited neighbors. We are currently visiting M and its unvisited neighbors are G and J. For the current vertex, calculate the distance of each neighbor from the start vertex. Using the information in the table, we can see that the total distance to M is 4 from the table. The distance from M is 4 plus 4, giving us a total of 8. And we can see that the total distance to M from A is 4 plus another 6, giving us the total of 10. If the calculated distance of a vertex is less than the known distance, update the shortest distance. Now, we don't need to update the distance of G this time. We calculated 8, but in the table, we already got a shorter path, so we leave that alone. On the other hand, the total distance to J that we calculated is 10. In the table, it's currently infinity, so we will overwrite it with the previous value. And since we updated the value of J, we are going to update the previous vertex for J. In this case, we visited J via M. Add the current vertex to the list of visited vertices. We won't be visiting M again. Visit the unvisited vertex with the smallest known distance from the starting vertex. This time around, it's G. For the current vertex, examine its unvisited neighbors. We are currently visiting G and its only unvisited neighbor is J. For the current vertex, calculate the distance of each neighbors from the start vertex. So performing the same calculation again, we found that the total distance from A to J is 11. If the calculated distance of a vertex is less than the known distance, update the shortest distance. Well, now that the value on the table shows us that it is settled, so we don't need to update the distance to J. Update the previous vertex for each of the updated distances. No distances are updated, so we don't need to do this either. Add the current vertex to the list of visited vertices. Vertex G won't be visited again. Visit the unvisited vertex with the smallest known distance from the starting vertex. This time around, it's vertex J. For the current vertex, examine its unvisited neighbors. We are currently visiting J and it has no unvisited neighbors. There's nothing to do, so we add the current vertex to the list of visited vertices. There are no vertices to visit, so our table of information is now complete. And that will be all for the Dijkstra shortest path algorithm. Thank you.